Hello everyone, and thanks for being my audience in this presentation. My name is Obilikpa and I am an academic staff at the Department of Mechatronics Engineering at Ekwueme Federal University, Ndufu-Alike, Ebonyi State. This work, titled the Design and Implementation of Robust Controller on a Novel MEMS force sensor, was carried out at the Laboratory for Dynamics and Control of Nanosystem, University of Texas at Dallas, United States, from March 2019 to September 2019, while I was a visiting research scholar at this institution. This work has two main objectives, which are to design robust controllers for the MEMS force sensor and to implement these controllers on Simulink and Unreal system setup. This sensor, in brief, is an electromechanical system, or simply MEMS, which has wide applications in mechanical, electronics, and biomedical systems. To widen the scope of application, a stiffness adjustment mechanism was incorporated in already existing design, which allowed the regulation of the stiffness of the samples being characterized while using this device to measure any substance. We have the view of the force sensor, that is the scanning electron microscope view of the force sensor. It includes the stiffness adjustment mechanism, although not shown on this view. And at the right hand side, you have the electrothermal force sensing components. The mechanical flexure is also incorporated in design to guide the probe. It is important to mention here that the device was fabricated in a clean room, and the design and fabrication are not included in the scope of this report. The operation of this device is of two types: the open loop and the closed loop force sensing. In the open loop force sensing, the displacement of the sensor probe is measured, and by knowing the stiffness of the probe, the applied force was determined. Whereas in the closed loop, a controller is included to receive the feedback. This feedback could be nonlinearities arising from the mechanical flexure, which the controller would then compensate. The performance of the sensor was determined using the setup shown in this slide. First, we have the MSA, the microsystem analyzer for data management, the DS board for analog to digital signal and digital to analog signal conversion, the voltage amplifier, and the DC voltage supplier, which was connected directly to the MEMS sensor being characterized, and an oscilloscope for viewing the input signal. During the experiment, the voltage of the stiffness adjustment mechanism was varied from 0 volt to 65 volt. The corresponding displacement of the probe was measured, and using this measured displacement, the identification was carried out. A technique known as AMAS method, which stands for auto-regressive moving average with external input, was employed to identify the dynamics of the nominal system of this varying adjustment voltage. As can be seen in the figure, the simulated value tend to approximate closely the measured value, and on the right hand side you have the nominal systems for 0 volt and 65 volt. The order of this system was seen to increase as the adjustment voltage was increased. Next is the control. Here, two control approaches were employed. You have the model reference adaptive control and the robust hedge-if-need control. Let me mention here that the essence of the control design is to ensure that the probe remains in its null or zero displacement position, so as to ensure that the displacement of the probe is robust. Okay, now in the first figure we have here is the system which is badly damped, and in control engineering, a badly damped system is an unwanted system. Okay, now in previous control implementation, which has already been reported in another work, a non robust control known as internal model control was approached to tackle this badly damaged system, and the result, as you can see, is presented in the second figure. Whereas in the last figure you have a resonance controller and the open system of this force sensor being plotted. In all, this system is not robust. That is, its operation cannot guarantee some specification. So due to the fact that for example, external disturbance can affect these non-controllers when they are used for closed loop force sensing, it is important to design or synthesize a robust controllers that will ensure that the specifications of systems are maintained irrespective of any environmental condition. That is the essence of the control design. Control approach considered in this work is the model reference adaptive control. Here, what is known as MIT rule was used to design this controller. The rule basically employs a cost function that depends on the control parameter. The control parameter, or what is known as the adaptation gain, is an important factor for this controller. The first figure you are seeing there is the response characteristics of the system and the reference model without the control, or without what is known as the adaptation gain in a MATLAB Simulink. Okay, now by varying the adaptation gain of this controller from 0.5 to 3, it was observed that the variation of this parameter causes the tracking error to tend to 0, and performance of the actual system approaches the performance of the reference system. Hence, the law is applicable to this system. Now, let's consider this table. This table shows all the specification of the systems with and without the model reference adaptive control for different adaptation gain. In this table, the settling time was observed to increase with increase in the adaptation gain of the controller within the selected range. Other properties such as the overshoot and the undershoot were eliminated using this controller. This implies that the MIT rule of the model reference adaptive control can be used to make this force sensor to approximate its reference value in operation. Hence, it is applicable to this system. Another important control approach employed in this work is the H-infinite control algorithm. The H-infinity is a well-known controllers for sensors and actuators. To use these techniques, a control designer first formulates the problem as a mathematical optimization problem and then finds the controller that solves this problem. Basically, the performance to be achieved, which may include error tracking, command moderation, disturbance rejection, and most importantly, uncertainties, which may be in form of noise, are expressed in terms of weighting function. And by employing this approach, the standard augmented controller with weighting, the controller is calculated or synthesized. To know whether the specified performance given to the controller will be guaranteed in any operating condition, a parameter expressed as gamma in the mathematical optimization formulated problem is used. When this value known as gamma is less than or equals to 1, it means that all the specified performance will be achieved, whereas when it is greater than 1, it means that only some performances will be guaranteed. For the force sensor with zero adjustment voltage, a system of order 4 was identified during the identification process, and the controller of order 5 was obtained during the controller synthesis. This controller has an optimum performance level of 0.81, which indicates that the controller is implementable. And to test the efficacy of this controller, the MATLAB Simulink was employed. As can be seen in the figure, the plot is showing the output response, which track perfectly the input response, and the performance and the disturbance rejection was also met using this plot. And finally, on this work, the controller which has earlier been determined was implemented on the real MEMS force sensor setup. In this setup, a pulse signal was applied to the sensor, and from the figure shown on this slide, the tracking performance and the disturbance rejections were guaranteed. Hence, this controller will be robust in any operating condition. The controller guarantees robustness, as has been expressed, good performance in terms of sensitivity, and provide high external disturbance rejection. Hence, the system will be stable in any operating condition, and this is the main essence of this controller. Conclusion: two robust controllers, namely the model reference adaptive control and the H-infinite control, were synthesized and implemented on the real MEMS force sensor in this work. Future work will focus on the dual MEMS force sensing, and the design and implementation of these controllers are also recommended. On this note, I would like to say thank you for being there throughout this presentation, and I would like to express my gratitude to my supervisor in US, Professor Reza, and his research team at Laboratory for Dynamics and Control of Nanosystem. For further questions and comments, you can reach me at the email shown on this last page. On this note, I would like to say thank you very much and God bless.